Okay, so we will continue um, where we left off. Just one small clarification. I was not aware that last time the other screen was not coming. So this is what I was drawing. Quickly we'll go through it again because it's quite important. We have two types of transistors. We have first the NMOS transistor and we have the PMOS transistor, and each transistor is going to have a size. So for now we look at the smallest possible size, and this is also not possible, as you know, W by L cannot be 1 because W and L cannot be the same for a transistor because of design rules, etc. And we are going to assume, okay, W by L equal to 1 is a unit transistor. And actually, if you look at the transistor, if you look at the length, okay, suppose for example in cadence you're using 180 nanometer technology, that means that the length of the channel or the length of the transistor that you see here, distance between these two terminals is going to be 180 nanometer. Okay, and that is also called as 2 lambda. And you cannot have W equal to 2 lambda, and that is something that you might have learned in the previous semesters. But W cannot be 2 lambda because of design rules. Minimum possible value for W is 4 lambda, and if that is the smallest possible transistor, obviously it cannot have a W by L equal to 1. So what we are defining here, okay, is that a unit transistor that is satisfying all the design rules, that particular transistor, the smallest transistor that is going to be fabricated, that particular transistor has size 1, okay, which means that the W of the transistor is actually 4 lambda. The L for the transistor, the smallest possible value is 2 lambda. So W equal to 4 lambda, L equal to 2 lambda, by definition is a unit transistor. And this could be PMOS or it could be NMOS. It doesn't matter. The design rules don't change for PMOS or NMOS. So there also the same transistor size, W by L equal to 1, means that it is a unit transistor whose W is 4 lambda, whose L is 2 lambda. Okay, and this is just again a matter of definition to make things a little bit simpler in the computations for us. And the next part of the definition is the resistance and the capacitance. We will start from the bottom. We have an NMOS transistor, and we already mentioned this. Resistance is R, this is defined by us, and the capacitance associated with this particular transistor is C. And for the PMOS transistor, the same size, okay, the resistance is 2R and the capacitance is C. And this is again derived from the NMOS transistor. This is not uniquely defined, and the reason, okay, is associated with the charge carriers. In the NMOS transistor, electrons are charge carriers. It's easier to move electrons, so the per unit resistance is small. So if I apply a voltage across these two terminals, I will get some current here, okay, and here I will get a smaller current, and the reason for that is it's not as easy to move the holes. We don't have electrons in a PMOS transistor, we have holes, and the holes, whenever we want to move a hole, we have to break a bond, and then the electron has to come into the hole, and which means that the hole has moved in the opposite direction, and that's more difficult to do, which means that the resistance associated with that particular transistor is going to be higher. So its resistance, we are defining this is going to be 2R. Maybe some other this thing might be, but for now we just assume that it is twice the amount. And if you look at the physical property, the actual physical property that makes us, allows us to decide these two numbers, is the mobility of electrons, mobility of holes. And you might have seen this when you were looking at the current equation. Current equation has that mobility term, and whenever you did numericals, if you realize the relation between those two, mobility of electrons around 2 times the mobility of holes, and all that also comes into the same relation here. The resistance of the PMOS transistor, the same size PMOS transistor, is 2R, and this you have to remember, okay. I might not say this every time, but if I'm just given an NMOS and a PMOS transistor, I'm going to assume that it is R for the NMOS transistor, 2R for the PMOS transistor. The second part, capacitance, does not change because capacitance is related to the structure. All the materials are the same for the NMOS and the PMOS transistor. The substrate is the same. Assuming that the doping is the same, everything else remains the same in terms of the materials, in terms of the insulator, etc. Which means that for both the transistors, for the same size, the capacitance is going to be the same, and that is why we C and C. So this slide is very important, this diagram, the resistance and the capacitance associated with unit transistors. Unit transistors, W by L equal to 1. It could be PMOS or it could be NMOS. These are the things that we have to remember. Okay. So that is the last point that I mentioned here. It could be 2R or 3R depending on the actual fabrication. And for now, we are just going to go with the default value 2R. Okay, we will not change that. And next thing is, what is the relation between these numbers and the R and C? Obviously, W by L equal to 1 is one number, and we will never always stay with the same number. We might have a transistor whose W by L equal to 2, W by L equal to 3, etc. So the natural question is, if I increase this W by L equal to 1 is the unit transistor, smallest possible transistor, but it can be bigger than that also. It can be 2, 3, 4, etc. So as I change this W by L to higher values, what happens to the resistance and the capacitance? So for that we can get it in a few ways. One way to do it is to remember that the current equation is has a term W by L, and the current equation, the W by L term, is directly proportional to the current, which means that if I double the W by L, for everything else staying the same, supply voltage, etc., the current is going to double. And this is true for NMOS and PMOS transistor, which means that if I double the size of the transistor, okay, I am making the current double. That's one way to look at it. But also, if you look at the width of the transistor, so let's draw the layout of the transistor, which is going to help us in determining this relation. So if I look at the layout, okay, so here is my transistor, and this is L, and this is W. Okay, and if I change this W, so if I say double the width of the transistor and keep the length the same, okay, so effectively I'm going from one value of W by L to double of that. Okay, so we have to remember where the current flows from. Current flows possibly in this direction. This is my I D S, the main current. Okay, there are other parasitic currents, we will not worry too much about that, but this is the main current flow in a MOS transistor, drain, source, drain, whatever. So IDS flows from this side to this side. In this case also, IDS flows from this side to this side. Now can you tell me, so this, let's say that here my W by L is some number, and here I have approximately made it double. Okay, so the current is going to double, and what is going to happen to the resistance R, which is, if I define it as VDD by IDS. One way to look at it is, we know the equation for IDS. If the W by L doubles, the current is also going to double, which means that the resistance in the first case versus the second case. What is the resistance of this transistor? The resistance of this transistor, what is the relation between those two? That is what we are trying to find out. In particular, we just want W by L to come somewhere in the picture so that we can find out what is the relation between W by L and the resistance. And since we said that current is proportional to W by L, if we can rewrite this as, so this tells us this final relation, resistance and W by L are inversely related to each other. If I make the resistance of the transistor double, okay, sorry, I don't change the resistance directly. If I make the W by L of the transistor double, then the resistance is going to become half by the same ratio. If I make the W by L 4 times, then the resistance is also going to reduce by 4 times. So that is the relation that we want to see. What is the relation between resistance of the transistor and the, okay. Next is the capacitance. Now a capacitance is not related that much to the current flow. It is more related to the size of the terminal. So if I look at a transistor, I am interested in three capacitances. One is the capacitance related to the source substrate junction. Other is the drain substrate junction. Those are the diffusion capacitances. And the third one is the one that is related to the gate capacitance. So W by L equal to 1, this is our unit transistor. So by definition, on all the three terminals, the capacitance is going to be C. Okay, and this is my definition. Per unit transistor, that is W by L equal 1 is the unit transistor, and associated with that size is a capacitance C. Now if I change the W by L, the equation for capacitance is C equal to A epsilon divided by D. And in these capacitances, D is the distance between the parallel plates. So for the gate capacitance, it is the distance between these two. Okay. And if I'm changing my transistors W by L, that's not going to change because that generally stays the same for any particular technology. So the D is not going to change much. Similarly with these two also, if you look at these two capacitances, the depletion region width under reverse bias, that is going to determine the distance between these two parallel plates, and that generally remains the same also. It's not going to change unless I change the reverse bias, which means I change the power supply. So D generally will not vary with the size of the transistor. And epsilon again is a material parameter. If you are with silicon, it stays the same for these two transistors. It's slightly different for this because in this case the material is silicon, which is in between the parallel plates. In this case it is silicon dioxide, which is a slightly different material, but let's not bother about that for now. That's not going to change much. So the A term, okay, there is the size of the capacitor, that is the area of cross section, that is the one that is going to change. And in this case it changes linearly, which means that if I go from, okay, W by L equal to 1 to W by L equal to 2, we are going to assume that all the capacitances change from W by L equal to 1 to W by L equal to 2. Okay, that is the relation that we have to remember. The capacitances are directly proportional to the size of the transistor. If the W by L increases, capacitance also increases. Minimum possible value, like we know, is C, because that is what is defined by a unit transistor. We can't have anything smaller than that. As we keep making the transistor bigger and bigger, the capacitance associated with the terminals, that also changes. Okay, so if WL is 2, it's 2C, and so on. So that is one very important relation that we have to have between the transistor sizes and the capacitance and resistance. That is the transistor size as determined by W by L, and the capacitance and resistance that changes according to the W by L. So what is the independent variable? The independent variable is W by L. That is the one that we have to determine first, and based on the definitions that we have, we can determine the resistance and capacitance that is associated with each of these transistors, and that is what we see here also. If the W by L is increased, okay, and naturally also we are making the transistor wider, so it's more easy for the current to flow, which means the resistance will reduce. And similarly, if the W by L is more, then the size of the capacitance, parallel plate capacitor model, size will increase, which means the capacitance also increases. And that is the relation that we also have to remember. Resistance directly proportional to W by L. Okay, resistance inversely proportional to W by L. Capacitance directly proportional to W by L. Now the next thing, okay, so we can calculate these for PMOS transistor, we can calculate these for a NMOS transistor. If you want, we can just do a small example. Okay, take a NMOS transistor and a PMOS transistor. Now we will make a small table, okay, and we will write down the values for W by L for each of these, and associated with that we will write the resistance and capacitance, and we will start with 2, and we will also do, for example, W by L equal to 4. And first we will look at the NMOS transistor. R, what is the resistance associated with this transistor? Okay, and what is the resistance associated with this transistor? And W by L equal to 1 is the one that was defined, okay, which means that if we have a new transistor, which is this NMOS transistor, whose W by L is double, okay, it is going to be having a resistance of R, which is the predefined value, divided by 2. Okay, where did this 2 come from? It's exactly this number. Might not be exact, but the relation is what we are worried about. If the W by L is double of a unit transistor, the resistance associated with this NMOS transistor, that is, I'll have some R that is going to be equal to R by 2. And similarly, the capacitance, that is directly proportional to the W by L, so that is going to be 2C. Okay, and this is for the NMOS transistor. And if you look at the PMOS transistor slightly different properties because they have holes, okay, and here a W by L equal to 1 means the resistance is 2R, and this is the per unit resistance of the PMOS transistor. So if the W by L doubles, the relation is the same, but the per unit resistance itself is 2R. So I am going to get the resistance for this transistor is 2R divided by 2 equal to R. Okay. And the capacitance is going to be 2C. That is relatively simple. And you can do this again. If I have a much larger NMOS transistor, this is going to have a resistance of R by 4, okay, and capacitance of 4C. And this transistor is going to have a resistance of 2R by 4, okay, and a capacitance of 4C. That stays the same. You have two different transistors. This is W by equal to W by equal to. These are the numbers for the NMOS and for the PMOS transistor. So this is very important to remember these relations. What are the per unit values of resistance, which is what we have written here for the MOS transistor, and similarly for the NMOS transistor also. Just for the sake of completion, I can write it again. W by L equal to 1 implies that it has a resistance of R, okay, and that is why we have R by W by L. Here also R by W by L. So if you want to make this more general, okay, we can do that. For a NMOS transistor, the resistance equal to R divided by W by L of the NMOS transistor, and similarly the capacitance equal to C multiplied by the W by L. And these are the definitions. And once we have defined this for the NMOS transistor, we can slightly modify it to get new values for the PMOS transistor, which is going to be slightly different because the per unit resistance is 2R, okay, and instead of N we will have a P, and that is the W by L of the PMOS transistor. Okay, so these relations are very important, and they are going to help us a lot because we don't have to worry about the actual technology node. We just have to worry about the W by Ls of the transistor, which means I can use the same design over multiple technology nodes. I'll obviously get new numbers based on the new values of R and C for each technology node, but it makes calculations and it makes scaling new designs, etc., very easy. Okay, so stop here